Alright, so hello and welcome. We're here again. Oh boy. So, I have been struggling mightily with this question, and I came up with an idea for a solution, and unfortunately, I don't think it's going to be correct or fast enough. But we could try it. Let's give it a shot. I think what I'm going to do, I've been on this for like almost a week now, this question, just pondering it, and it's kind of a lot of thinking, quite frankly. It's a lot, and I think maybe it's not worth spending that much time trying to work my way through it. There's like over 1,000 other problems to look at, so I don't want to waste too much time on this. I've already spent a few days. Usually I like to give, I don't like giving up too easily, but sometimes it's just beyond you in terms of there's just something you're probably just never gonna think of that's involved. So here we are. The question is substring with concatenation of all words, hard, C++, part 2. Let's look at the problem again. Yeah, I've been thinking about this for a while. I've been like struggling with this, I would say. I think it's fair to say I've been wrestling with this for a while now, and I've also been kind of having a hard time doing anything else, I guess. I mean, I don't know, not really like doing anything else that's productive, because I keep thinking like, well, if I'm going to do something productive, then I should think about this problem, but the truth is like I can't solve it, right? Like I don't know the answer. I just don't know it. Yeah, I probably quote unquote could solve it given a long period of time, but I think that's maybe too long. Like I should probably do other things with my time. I probably think that's the best use of my time. So those are my excuses for basically today. What we're gonna do is there's a solution I thought of that might work. I think it's gonna be too slow, and then we're gonna look at the discussion for a solution that does work. And that's it. That's it. Because sometimes you run into stuff. It's like I don't know how much time you should spend on this. So the idea that I had is as follows. I don't think it's gonna work, but we could try it. So what we're gonna do is we're gonna build a trie, a prefix tree rather. Yeah, a prefix tree, or otherwise known as a trie, trie. We're gonna build a trie, certain type of trie called a prefix tree, and we're going to use this tree to keep track of the words that we've seen so far. And we're going to use a depth first search. So the state of the trie is going to change as we see different words. So part of the problem with this question is the issue is if the words have prefixes. So in other words, one word, 130 character word, could have up to 29 other words that are prefixes of that word. And the problem with that is that the approach that I'm going to take, the problem is that you can effectively partition a sequence of characters with different words based off of like the prefixes. So like you could have something like A, B, C, D, E, and you could have that partitioned into A, B, C, D, and E, or A, B, C, and D, E, or it could be A, B, and C, D, E, or A, B, C, and D, E, right? There are all these different, like all of those words could be present in our word string, our list of words. And the tricky thing here is that like there are different scenarios you could see where you'll run into problems depending on like which of these words should we consider in each scenario, in each case, while you're reading through the string, right? Because we're trying to figure out, like which words are being used in that string. And yeah, you run into a lot of problems. So one way to address this is to use a depth first search, and just on every prefix that you see, you could either take that prefix or not, right? I don't think you need to do this with whole words. I think you only need to do it with prefixes. Yeah, so whole words, when you see a whole word, you should take that word. Because it only really matters for prefixes, right? Because if you keep going, you take more characters, consider more characters, then you're no longer like considering a word. Yeah, like really the suffix, the prefix tree is supposed to just basically split our string into the words, and keep track of which ones we've seen. So now the problem is, right, the prefixes, strings that are prefixes of each other, you can either decide to stop at that prefix or continue to the whole word. And this is where you kind of get into some trouble, because you can use a depth first search and say, okay, we're just going to recurse on all those possibilities where we either take the word or don't take the word, right? And what ends up happening is that I don't actually know what the runtime of that is. I think it could be pretty slow. I think it could be like exponential with respect to 30, but actually you can't really have, I want to say something like you actually don't have that many possibilities in practice, something like that. Like I couldn't really think that all the way through. I was having a hard time with that, but I'm going to go with a depth first search just to be certain that it's correct. And then what I'm going to do is I'm going to say, okay, at each index, we're going to progress until either A, we get all of the words, or B, we hit a point where none of the words fit anymore. All of the possible, sort of prefixes and I guess like paths, other paths, like the entire depth first search tree has been searched, right? For a certain given index, and then we just go to the next index and repeat it and do the whole thing again. And just use the try, and the try, we're going to at each try, like you could have duplicates of these words too, in theory, right? They didn't really say if you could have duplicates or not. Let me check actually if you can have duplicates or not. I'm assuming you can have duplicates. So yeah, no, actually it did say you can have duplicates. Yeah, this example had duplicates. This one did. Yes, you can have duplicates too. So we have to just use our try in such a way we also have duplicates. But yeah, excuse me. So that's the approach. And if M is sort of the total concatenation of all of these 5,000 words, obviously M has to be bounded by 10,000. Then it would, I think the runtime could be like O of n times M times K, where M times K is some constant K, which is some factor where I guess it's like, it's not the number of branches, because that's the thing I'm kind of struggling with. I'm not sure if it's exponential, these depth first search, this depth first search approach, or if it's like just some constant times M, because your words are limited in terms of like how the number of prefixes you could have are limited. So there's like a sort of I guess it would be like a limited branching factor, something like that. I don't really know. I'm a little bit confused. Like I'm not sure. I'm not really even sure what the runtime of this would be. I think it's like technically n times something exponential, but I really don't know. With depth first search, it gets kind of confusing sometimes to analyze the runtime. Can be challenging. Let's just say I don't really know. I think it's probably overall not fast enough, though. That's the problem. I think it's correct, but not fast enough. And I couldn't really think of something that was better that was also correct. I was struggling. So yeah, I'm just gonna go with this and see how it goes. My basic assumption is that like the test cases themselves will be simple enough where this approach, even though it's not really a good approach, will still work. I could be wrong about that. I mean, I've been wrong before. But I'm going to try it, see how it goes, and then just think of the discussion. I don't have too much confidence that we'll be able to solve this one, though. I think there's something happening here that I'm just not aware of or don't realize. Yeah, so I'm going to go for it. All right. So first things first, we're going to have a DFS. We've got to build a try. So we're going to have our just prefix tree, and we're going to use we'll use a struct, call it Trinode, and actually let's do there's actually case conventions. I'm curious about the case conventions. Google has a style guide. It's useless. Alright, I'm not gonna worry about it too much. Whatever. Let's not get so hung up on case conventions. It's fine. Trinode. Alright, so Trinode, we want to say it's going to have a couple things. We also have a hash set too. I'll explain that in a moment. What that's going to be. Do we need a hash set? I actually don't think we do. I'm thinking about it. Let's see. Let me think here. Yes, we do need a hash set. Yeah, we do. I'll explain that in a minute too. Need a hash string to Trinode. It's a pointer, Trinode pointer. And let's try using shared pointers here actually, because recently I was quizzed on the memory library in CPP, and I wanted to review that. Memory. General utilities, strings, containers, iterators, ranges. Somewhere around here is the memory. Where's the memory library? Huh. What? Oh, it's utilities library. Okay. Where's that? Look at the table of contents over here, and I'm looking for where's my memory library. What's going on? Iterators, containers, strings, diagnostics, general. Oh, there it is. General utilities. Ah, there we go. Okay, smart pointers and allocators. This is in the general utilities. Yeah. We're looking for the memory. There we go. Okay, that's what we want. Dynamic memory management. Yeah, I was recently quizzed on this, and I didn't really know what was going on because I don't use unique pointers, shared pointers very much. Interesting. So let's use shared pointers. Alright. Make shared p derived. Shared derived as a pointer to base. Threads. Interesting. Shared ownership between 3 threads and released ownership from main. Get, use count, join. Huh. Excuse me. What does this do? Make shared. Structs an object and wraps it in a shared pointer using args to the parameter list. Oh, okay. So we can make shared. So it's a shared pointer base pointing to a derived object. So we can make shared derived. So we can do make shared of try, something like that. Let's do standard make shared of Trinode and we're not going to give it any. What I want to do is use a unordered map, not of tried nodes, but of shared pointers. I just know this is a shared pointer. Let's try that. Shared pointer to a trinode. Could do that. Now I wonder, are these supposed to be pointers or the objects themselves? Looks like they're not pointers. Okay. Interesting. So that's kind of nifty. So it's a shared pointer. All right. But this is the object itself, not a pointer to the object. That's interesting. Okay. So, all right, we're gonna say word to try map, something like that. Simple thing. So we have our map, we have our try nodes. We're gonna build the try. Process for the pre-processing steps. So we'll have int word count. We'll just say 0. So I think we want, yeah. So we'll say max or total word count. Total word count will be a const, and then current word count. It's not const. Okay. And we only set this once. I don't know if you can. That's a good question too. I don't know if you can make this const. I only set it once when you construct the object. Okay. Total word count, current word count. We have children. So we're going to have standard vector of children. Really, we're just practicing using the shared memory conventions. Since we're not actually gonna put anything on the heap. As it turns out, nothing's going on the heap. It's all going on the well, maybe I guess it would. Actually, the shared pointers would go on the heap. So all right, anyway, so standard vector of trinode shared pointers. Children. And what's interesting about this is these are other trinodes, but they have it's actually a map. We're gonna use an unordered map. So actually, yeah, we could use a vector, that's fine. We're gonna use an associative array, or you could use an associative array. Actually, here we use a regular array by using each child is going to be related to one of the lowercase English characters. So actually, instead of using an associative array for the characters, we can convert the characters to integers and just have 0 through 25, right? 26 integers. So this actually would be an associative array still. But yeah. So you have children, which we're going to map to other trinodes, right? So you have current word count, total word count, and the children. And we should also store the word at this point too. Whole word. Yeah, we should store a word there. So that way we don't have to go figure out which word it's supposed to be. Just the node already has it there. All right, so yeah, so we're gonna build the prefix tree structure, pre-processing the words. Okay, so the way this is going to work, we're going to have the root. So we're going to have standard shared pointer trinode root is going to be standard make shared trinode, right? we're going to say so for each word, we'll have the first character. So the way it's going to work is you're going to traverse the try structure with your current word from the root. So we'll say for const string word and words. I'm going to say for const character C in each word. We're going to start from the root. I'm going to say current position. So we're going to say, so it's a shared pointer Trinode. You can maybe say something like, alias shared, or using, is it using? Typedef. Standard shared pointer Trinode. We'll just say stnode, shared Trinode, shared tnode, something like that. Yeah, just say stnode. So stnode, that's a little bit easier than writing out all of this. Okay, so current is going to be equal to the root, and we're going to say for each character, we're going to say if root children, so if root children, if we have this, so we're going to say int index is going to be, this is going to be const too. That could be the character minus a converted to an integer. And then we're going to say if root of children, so we get the children, we say index. Now this vector, it should be the null pointers initially. We create the nodes, so maybe we should just have like a Trinode constructor here. We'll just initialize the children, the word will be empty. Children, I think this is okay. We could do, we don't really need a constructor if we add the code over here. We could just say children of, it's 26 children, and they're going to be null pointers initially. I'll do it that way. Can we do it that way? I don't know. We'll find out. Okay, so now we want our root children index is not equal to the, so it's equal to the null pointer. Then we're going to update our current to this new node. We're going to construct this node. Otherwise, say current equals, root children index. Okay. So yeah, we're either gonna jump to that node that we've already created for this character, or we're gonna create that node, right? So we're gonna say new node. New node. Oops. New node. Excuse me. New node, and we're gonna say new node dot current word count. I don't actually know But that should how to set those things. Well, then the current word count should always be 0, but the total word count is a question. That's actually a very good question. So I'll come back to that in a moment. So children. So actually, we really could actually just set the root children. Not root. It should be root, by the way. This should be current. Current children of index should be equal to this new node. Now there's some issues here. There are some issues here. One issue is the last character. That's the node we want to modify. I mean, one thing we could do is just every let me think about this for a second. So also I have to address the prefixes too here, which is kind of a tricky thing. Let me think. Well, I mean, one thing you can do is you could just loop through the words again. Nah, I mean, that's not a good idea. Yeah, okay. Interesting. Let's do it this way. Yeah, that's a better way of doing this. So this is the last one. So if I is equal to w, that's size minus 1. Then, oops. If I is size minus 1, then we can say word, so new node dot word. So this is actually a pointer. So word, new node word is equal to w, new node total word count plus, and or just plus equals 1 is probably a better way of doing it. Plus might be kind of confusing. Yeah, do plus. It's fine. Yeah, I think that's fine. It's actually the same thing on both of these. Oops. And actually, it's not the new node, it's the current. Yeah, so we're going to say current equals, yeah, well, so in either case, current is going to be set to this root children index. Create a new node there. It's a null pointer, so it'll never be the null pointer. And then we can update current to that in these cases. Yeah, and re-updating the same word is fine. It's redundant, a little bit of redundant work, but we don't necessarily need to worry too much about that. Well, I guess, yeah, it's probably better. Yeah, we would have to put this part inside here. I think it's not really much better. So, okay, so this will create the try, I believe, and we also want to update our mapping with each word. So we also want to update this guy, word to try map as well. Okay, so that word is going to go to current, right? We're going to associate that each of those strings with that ending node, that current node, right? And so having a total word count supports multiple, or basically supports duplicates. All right, I think that's how we're going to build our try. Come back to that shortly. So we could start with excuse me, we'll just return something like this, a vector of a 0. See first if it compiles, if I made any mistakes here. Compiler, okay, that's definitely an error. That is most definitely an error. Interesting. Oh, wait. Oh, this is itself. Parameter declarator. Can we not do this? Maybe that's the part that's wrong, actually. Might be that we just couldn't find the shared pointer. Oh, okay, sure. Gotta go ahead and just put this at the top. Because this is kind of annoying to type out. Yeah. Something like this. Nice. I guess not. Okay. Alrighty. Can't use my type def in there. That's okay. Good. Okay. Kind of annoying, but it's okay. Alrighty. Oh, alright. Let's see. Runtime error, nice. I made a mistake. Oh, no. Oops, not root. That's a mistake. Man, where are all these mistakes coming from? I don't know. I guess it's kind of unusual code for me to be writing. I don't work with tries too often. Okay, compiles. Sweet. Compiles and executes. You can imagine that. Now we're going to use this prefix tree. So let's try to execute this on this prefix tree. Let's try to find. So we're gonna have our DFS, and we're gonna run that at each index. DFS is going to return just going to return true or false, and we're going to use our prefix tree, which is really just the root. Think here. So what do we want to do? How are we doing on time? 34 minutes. Yeah, this is a doozy, man. Even if, this is not even going to be correct too. Is the thing. It's hard. The worst part of this is like not necessarily a correct answer. It's just frustrating. That's always good. Okay. So what we want to do now is yeah, well, we'll just call we'll just process the DFS. Okay, so this is going to be interesting. This is going to be interesting. So processing the DFS, we're going to take each word. No, it's not each word. It's an index. So we're going to say current index, right? And this is a const value. Take our current index. We're going to have a Trinode also. So I have stnode, right? Current node. And we've got the state of the prefix tree, which is going to be changing as we go. We don't need much more than this for our DFS, I think. I think that's all we need. We just need the state and these two values. Now notice we can't really memoize because we have this state variable, this prefix tree that we're using, which really we are going to modify this. We're going to contain some of the state in the prefix tree, and we're going to modify the prefix tree as we go. So we can't really like memoize too easily this approach. I mean, maybe it's possible, but I don't really know how exactly to do that. The next thing is we have our current index, current node. What do you want to do? Oh, this function. So we have somewhere along the lines we have our total words. Now I'm not sure exactly how I want to manage this part, but what I'm thinking of doing is once we have the total number of words, once that's correct, then there are a few things. Let's just say those are like base cases we'll have. We're going to use for our base cases. We have at least a few different base cases. Yeah, I would say that's a tricky thing. So base cases. Yeah, we have different base cases. Or not even base cases, but yeah, some base cases. Okay. So we'll have a total. That's fine. That's okay. We can have a total. So int total. So if total equals the total. Oh, so that was supposed to be plus over here. I forgot about that. Yeah, so there's a total word count for that particular trinode and then a total word count overall, right? And if we hit this, if our total here reaches total words, total equals total words, then we return true, right? Then that's it. We can just stop there. If we got all of our words. Let's do it this way. Total words 0, and I'll do it this way. This is one way of doing this. May or may not be the best way, but one way. Excuse me, this is also going to be a const, I think. This might change this current node. Oh, I think it's also const. I think these are all basically const. I think that's fine. Might have to modify that later. So that's So first we're checking if we have the total. Then we're going to say if current index is greater than We also have s here, string that we're processing. Current index is greater than s.size. That will return false. Right, if we haven't reached the total, we've reached too far. Now we're going to say character C is going to be, this could be const, or yeah, character C is going to be s current index, and then constant int C minus A, and then we're going to say, that index is just useful for us later. We're going to say if current node children of index is equal to the null pointer, then return false. Right? So yeah, we can just stop there, right? Let me think here. So right. So basically, if that doesn't go anywhere in the try, then it would just return false. If it does go somewhere in the try, though, then we can continue and say so if current node, so we're going to say st node next is going to be current node children index. Let's do it that way. If not next, return false. It's a little bit more concise way of doing that. So we return false if not next. If next current word count is greater than or equal to the total word count, also return false. That's actually not what we want to do. We want to say if this is a, yeah, so I actually want to say if next word, let's do it this way, is not equal to an empty word. So found either prefix or leaf. Okay. Yeah, this is it's not too complicated to explain, but writing it down is, I don't know, translating it from my mind to the code is maybe not the most obvious thing, I guess. Okay, prefix or leaf. So if yeah, so it depends on what the word is. We're going to recurse regardless if we found a prefix or not, but it's going to be interesting when we find the prefix. So we'll say there's auto f, right? And this obviously at the end of things is going to return a Boolean. And we're going to say call f of current index plus 1, next the next node, and then I think we can actually make this const also, by the way. No, we can't. That's not true. Nope. Next, and the total plus equals 1 plus 1 and f. And we just say terminate early. if, then return true. By the way, at the end of all of this, return false. Well, we don't return false. Actually, I'll show you what we return. Okay, so we're going to recurse. So if we find a prefix or a leaf, then we're going to say, so it's not equal to an empty string, which we know that the words are not empty, right? We have that here, have that guarantee. Otherwise, we'd have to do something kind of different if it was possible to have empty words. So if our word is not empty on this Trinode, that means it's a leaf or a prefix. Then we're going to have to determine whether this is a leaf or not. So we can say at the end of this, we could just have a Boolean, say is leaf, it's just true in general. And then if we say if this is grandchildren index, yeah, so this current is leaf, it's false. Update. It is not aware, not a leaf node. Which is update the node such that it is aware that it is not a leaf node. Yeah, it's, yeah. Okay, some of these will be leaves, some of these won't be. So if it's a leaf, then, so if, because I need to do something with the leaf. So if next is leaf, then what we're going to do is update next to the root. Right, we go all the way back to the root. Otherwise, yeah. This is a tricky thing. This is kind of a confusing thing also. I gotta eat some food. Set a timer for a few more minutes. This is also a tricky thing. If we're processing a leaf node, basically the leaves are supposed to loop back to the root. But you might actually end. Yeah, well, that's a tricky thing. It's tricky thing. So first things first. So if we are not in other words, if we're a leaf node or a prefix node, then we're going to say check the first things first. If we're a leaf, we're going to do something with certainty, right? Well, that's confusing. And we're going to do something else if we're not a leaf. Let's actually do it that way. Oops. That's really confusing, actually. I think both of these we run this routine, but we'll come back to that in a second. We'll come back. Well, we can just say in both cases we'll just have duplicated code for now and then sort of fix it later. Let's do it that way, because this is kind of hard to think through, I think. So if we're not a leaf, let's say we're not a leaf, we're a prefix. All right. What we want to do is continue. But what we're going to do, if we're not a leaf, and that's actually kind of the key. Actually, the leaf part is really should go down here, I think. Possibly, I don't know. We'll come back to that. We'll come back to that in a moment. But suppose we're not a leaf. We're not a leaf. The more interesting part is whether or not we're not a leaf. If we're not a leaf, it means we're a prefix. And we're going to say, we're going to recurse with this recursion is going to assume that we took the prefix. The other recursion that we're going to do is assuming that we did not take that prefix. Yeah. So that's where the sort of branching is going to happen with the prefixes in our routine here. So if there is a prefix, we're going to increment the prefix count. So we're going to say next. A couple of things. Here we assume we take the prefix. So we would say the current word count, the total word count. We're going to increment the current word count. We're going to say, right, we're going to say if current word count is greater. Now that's also a tricky thing too. Where do we process each node? Like we could do the processing of the node up here, and then continue to the children. See, that's a tricky thing also. Is like, do we process the nodes up here, or do we process them down there? That's something that gets confusing with depth first search. Usually you process at the top, and then you sort of continue on your different children at the bottom, something like that. It's a little it's really confusing. It's very confusing the way that we're doing this. It's confusing. I don't know. There's sort of a mixing of things going on here. It's just hard to follow. I don't know, because sometimes you could do the processing before you jump in here. So let's process our prefix. Let's just see. Let's just continue with what we were doing, and then maybe we'll think of a way to clean this up later. So current word count plus plus, then we say if next current word count is greater than or equal to next total word count, then we have a problem, right? At that point we would return false. Wouldn't even continue down this path. Now, what's tricky about this is basically you don't return false. You just you just continue. So this is a little confusing, but it looks like this. You basically would return immediately that particular case is false, something like that. No, see, that's really confusing. out for a minute. Oh. Okay. Oh boy. Oh boy. Okay. Excuse me. This is not a very clean approach. It's kind of a simple, somewhat of a simple approach, but it's just not very clean. Kind of hard to explain. So I think part of the issue is incrementing, like, yeah, I think what we were saying before, like processing each node first, kind of like simultaneously both processing the nodes and then also sort of dishing out different sort of execution paths, like other recursive paths based on our depth first search, like our results of that processing. So, all right, let's keep trying here. Let's not give up too easily. I'm not giving up, but it's like, this is messy. It's like the logic is just, it's all over the place. It's too complicated. It's simple what we're trying to do, but it's just where you actually execute each part. The sequencing of it is kind of getting complicated. Right, because this actually is not what we want to do. Even this. I think we could just add a check over here too. To if. So current node. Current node. Could also say if this is not current node. That also could be meaningful. Total word count is greater than, if it's non-zero, the total. So current node total word count not equal to 0. Total word count's not 0, and the current word count is greater than the total word count. That return false. Okay. So if we see our prefix, we're going to increment the word count, decrement the word count, and run our something like this. We are going to terminate early, but also in our early termination, we're also going to need to fix the try each time. So if we see a prefix, we're going to increment our current word count on the next node, and then we're going to execute the next character on the next node. The total incremented by 1 as well. And I think that's it. If it's not true, then we're going to decrement. Okay. Is that right? I think that's right. I think that's fine. So that's if we see the prefix. And we also, like if this isn't a word to consider, then we're going to at the end of everything return false. But if this is if it's not a word, get a lot of spam calls. If it's not a word, then we're going to how are we doing on time? Got another hour. If it is or it isn't a word, we're always just going to keep going. If this is a leaf, then we are going to increment the count. Oh, see, that's a tricky thing. Oh, I see. Huh. Well, all leaves have words in them, right? All the leaves end on words. Just trying to think here. Really, this part we want to move all together. So I think, okay, we can do it this way. There's like a few different cases to consider. So it's not a word and it's not a leaf. Or rather, there is a word there, and then we're not dealing with a leaf. That means we're dealing with a prefix. Okay. So we're dealing with a prefix. This is what we do. If it's not a prefix, so if it is a leaf, then we're going to do some things. Otherwise, we're going to do some other things. So if it is a leaf, if it's not a leaf, then we just kind of recurse. Right, it's not a leaf, not a prefix node, it's an internal node. It is not a prefix node. So in this case, we just go to the next character with this next node. Total stays the same. Yeah, everything's sort of the same. If it is a leaf, then we actually, when we process here, actually we might want to put it over here. We would say if it's a leaf, if there aren't any children, right, then we might want to do that up here, actually, and not put that down here. Yeah, because what's going to happen is next is going to be the root. Like we're actually just going to jump to the root altogether. So we kind of do something like the following. So really you want to say if current node is a leaf. Okay, let's do it this way. So if current node is a leaf, then we're going to do some processing here. The next node is the root. We're going to go to the root. There's always going to be, we can always update our current word count. It's not current word count, it's the current node. Current node, increment the current word count. Go to the root, and we're going to say if this is tricky, man. This is a tricky thing. So we're not going to update the leaf. Yeah, so confusing. We will have already updated this leaf node. So we're just going to update every time we see a word. In one case we'll update, in the other case we won't. Yeah, if we decide to process the node. See, that's the thing that's confusing, is that if it's a prefix node, we want to start a whole different set of processing. If it's not a prefix node, then I don't know, I'm so confused. I think we process the leaf node. If it is a leaf node, then we update go to the next index, we go to the root instead, and we don't increment our total, we just keep the same total. So yeah, that's going to be confusing. We'll make the jump there to the root. And return false otherwise, right? So on the leaves, we kind of stop processing. We don't continue further down here. Confusing, I know. If we do continue processing here, though, we get our next node, so we're not a leaf. This really would be if it's a leaf right now, right? Whether or not, yeah, this would be a leaf. Somehow we don't really need that code, I think. Determine whether I found a prefix, right? So we know. So that's confusing too, because this itself could be a leaf or not. We don't really know. I want to say, yeah, the tricky thing is, oh man, that's so confusing. Do we even need this? Where are we going to do this processing? How's this going to work? Oh, it's such a headache. This is, okay, if the next is a leaf, then if it's not a leaf, then we have a prefix, and we want to process here. Yeah. Determine whether I have found or process a prefix. A new recursive search. All right. I think, yeah, so if we're not a leaf, if we are, yeah, if we, oh, so annoying. This is so annoying. If we have a prefix, oh dude, my brain's starting to mush. I'm trying to think about this here. Well, there's a few different possibilities, right? So if you find a prefix, you have a new recursive approach. If it's not a prefix, there are a few different other things to do. So if process next node if it is a leaf node by incrementing count Leaf nodes always have. Always contain the end of a string of a word. So if it's a leaf, then we're going to process prefix node, leaf node. So if it is a leaf node, we do a similar thing where we say if next total, but we're going to, oh man, my brain, man. Do we, once you reach a leaf, I think you return false if you don't return true. Yeah, because, well, that kind of goes back to what we're doing over here. We have our leaf nodes. It's so confusing. Yeah, where we set up our next could be a null pointer as well. That's very confusing. Okay. because the problem, yeah, that's really confusing. Okay, I don't know. I'm not really sure. I think we say next current total words plus plus, and then decrement next current total words. Okay, something like this. This is confusing as it gets. I'm actually not sure what to do about this one, quite frankly. Current word count it should be. Yeah. And then I want to say something like, really, you should increment the word count on the node itself when you're processing it. I think maybe that's better. And yeah, I think that's better. So let's do this. So if current node word is not equal to this here, then we'll do this other processing. And we don't need this anymore. We're going to say we're going to increment our current word, current node, current word count, plus plus, and then now, do we decrement at any point? See, that's the thing that's also confusing. Like, after that's so confusing. Visibly and audibly frustrated. I want to, so here's the problem. I want to update the data structure, but I'm also looping through the same data structure that I'm updating, which makes it so confusing. Yeah, that's part of the problem. That's part of the problem. Right. It's good. Why? 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 Because the question then becomes, do we change the state after we process the node, while we're processing the node? Like, when do these state changes occur, right? Because you can process, right, because we want to process the prefix node. Yeah, see, that's why it gets so confusing, is because you actually don't want to do this here. You want to perform the check here at that node, but before you, yeah, oh, dude, this is so confusing, unnecessarily confusing. I don't know if it's unnecessarily confusing. I think it has to be this confusing because we're trying to. Let me just sit down for a minute. Just take a deep breath. Excuse me. I need to go eat some food too. I wasn't thinking this was gonna take so much time. Brother, why is this so hard? Okay, let's think about this again. Let's try this again. So, what we want to do is well, when you come across a prefix node, so normally what you're going to do is you're going to recurse on the child node, the correct child node, if it exists, and return that result, right? That recursion. When you see a prefix node, now you branch into two different possibilities that each of those could return true. And if either of those return true, you also return true for your function. Now, the tricky part though is that the node processing and which node you jump to and all of that gets very confusing, because you're also doing another thing where when you see a leaf node, you're going to jump back to the root node in a kind of epsilon jump for processing, right? So you're going to, where exactly does that happen? Yeah, excuse me. That's also kind of special. So let's consider only a prefix node. Let's do it that way. Let's do like all of the logic that we're gonna have for a prefix node, and then all of the logic for a leaf node, because those are really the only two nodes, and then all the logic for something that's not a prefix node. So we could do it that way. We could say process a prefix node by beginning a new recursive search and continuing the previous search. Process the next node if it is a leaf node, and then finally process an internal node that is not. And then we're going to say process an internal node that is not a prefix node or a leaf node, Excuse me, there's 3 different cases. In each of those cases, you do different things. That's the crux of it here. Yeah, this doesn't really make sense anymore. We'll just say if the current word, yeah, it's not equal to null pointer and not equal to empty set, then we just check. Come back to this, but at no point should we. Yeah, this is fine. This check is fine. This doesn't really affect too many things. Okay. Whew, excuse me. So, all right. So if we see a, and then we're actually going to end all of these with a return false. Leaf is always going to have this true, and then this is if it's not a leaf, and it's not. Right. So these are different from each other. Okay. Excuse me. All right. So if we see a prefix node, we're going to call this routine, and then we're also going to call a similar routine here. We're going to say current index. So we know it's a prefix node. So current index next is the same total. So total plus 1. We don't count this node in this instance, right? So that's why our word count was decremented. So we don't count it here. So we have two different routines that we execute. Yeah. That's if this node that we're operating on is not a leaf node. Now it's really tricky because it's not that the current node is a leaf node, it's the next node that we're jumping to. We're going to process that node by incrementing the word count and then decrementing the word count when we're done. That is a tricky thing. That's a tricky thing. And part of the question is, should this incrementing of the word count happen inside of the processing of this node? That's kind of a question, because we could technically put that at the top here and have all of the nodes that have a word there increment the word and then perform this check and then decrement the word afterwards. But the problem with that is, I think, terminating early, right? Because terminating early on a false is not going to see that. Yeah, that's part of the problem. So we terminate early on a false, we don't end up decrementing this current word count, which is a problem. That's kind of why we need to why we want to structure it this way, is because we're terminating early on a true, but a false we're going to keep going. And so if we increment something, we want to increment it beforehand. That's kind of I think the tricky part. I think that's what's kind of tripping me up. Also, if we see a leaf node, so our next node is a leaf node, then, and obviously this will be true also, then with a leaf node, we do a similar thing, but now the question is, we should actually jump the next node. We should actually jump after processing here to the we make our epsilon jump, right? So this is also super confusing, because now you wonder, like okay, it's pretty simple what to do with a prefix node, pretty simple what to do with an internal node. Right, our next node is not a leaf, so then we just continue, right? We don't increment the total, we don't increment the total word count, we just keep going. What's hard about this is, what if it is a leaf node that you're looking at? So now you're looking at a leaf node. Now you do need to increment the current count. You have to decrement the current count afterwards if it's doesn't work out. But when you jump and your total increases, right? But the problem here is and you process this current index value, right? Go to the next character. This should actually jump to the root, believe it or not. This actually should jump to the root. But what's weird is like the logic to check whether, like check the current node and the current count, total count, you still want this to happen. So that's the thing that's confusing. You actually probably want the epsilon jump to happen inside here, right? So you'd want to run this routine, and then if the current node is a leaf, then we perform our epsilon jump. Yeah. So if the current node is a leaf, then we say, we don't increment the current index, by the way. We don't change the current index. We just epsilon jump to the root. Yeah. So the current index doesn't change, root doesn't change, total doesn't change. We just, or rather, yeah, we just jump straight to the next node, which is kind of interesting. Kind of interesting. And what's interesting about this too is we jump in such a way that we don't consider the rest of sort of what the possibilities here. We would just return false immediately, sort of terminate early. Like this is tricky too. Like this is not the most obvious thing why you would need to have this here also. The reason for that is the rest of this is not even a consideration. There will be no next node. That's sort of what the next thing you would do is you would say you could have your other check. I think there was a check I had before. If the next is empty, but in all these other cases, next shouldn't be empty. The only time it could be empty is here when we're a leaf. And oh no, actually I'm wrong about that. Oh no, wait, no, we do need this. I'm wrong about that. Yeah, actually we do need that. It could be just that the, I mean, yeah, no, yeah, no, I'm fine. I'm sorry. That's actually, this is correct. This is really confusing. Just really confusing. And what you're going to do, by the way, is you're going to run a loop at each index. So for int I equals 0, I is less than s.size plus I, and we're going to say, so we say a vector of integers ret, return ret. So if DFS of DFS ret pushback I, and we're going to have some other values here. Current index will be I. We'll start off at I. The current node will start at the root. Total will start off at 0. And DFS is our recursive function. Okay. And then we're just going to clear the try for each DFS routine. Okay. And that is going to look like the following. So that's each st node for a string. So word to try map is what we're going to use to reset. I'm going to say something like the following: for const auto p in the word to try map, which gives you w current, so word to try. We're going to say stnode p, or t, we'll call it, will be p second. Now we're going to say t current word count equals 0. So reset all the word counts back to 0. That's really it. I don't think that's totally correct. I think we might be missing something. But we can run this, see what happens. Total words. Oh, total words. So, I don't know. Oh, it worked. Hey, sweet. Neat. Runtime error, okay. Alrighty, which one? Which one caused errors? How are we doing on time? Hour and 30 minutes? Overflowed. Okay, let's try to find out where that's happening. Whoops. All right, let's give it a shot. Let us see. Let us see. That's a lot of errors. Okay. Interesting. It would just print the current node's address. Are we getting into loops? Like what? Where is this runtime error happening exactly? I didn't really name these nodes. Didn't really identify them in any way. Well, we could do something like this. Current character. What could be happening that this is causing somewhere there's integer overflow? I don't know. Why would that be happening? Okay. It says word GGOOD GGOOD word good G O R D G O O D G G O O D G O O D G O O D G G O O D B O O D G O O D B B E S T W W O R D, and somewhere here. DFS programs can be really difficult to, recursive programs can be really difficult to debug. By the way, can be quite difficult. What is the issue though? Addition of unsigned offset overflowed. Where's that happening? Like, can we just get okay? Like, which line of code is causing the issue? Error 1, error 2. Then we can get some sense. So it's between error 1, error question mark, error question mark. So error 1, and then twice this function is called. I'm going with this 2, make this like 20 and 30, and then we'll put some errors in between. Make this one 10, make this one 15. So right at the end there's error 15, error 20, and then somewhere here is, can we do error 25 maybe? Errors maybe not the right, maybe a misnomer here. If we just say debug 20. Error 20, okay, so we don't get to 25. How about 21? Do we get to 21? We do, okay. So it's somewhere between 21 and 25. Let's make this 20. Let's make this 23. Is the offending line of code. Looks like it's this one in between. Okay, so we don't make it to 23, which means this is the issue. Oh, what's this index? That's interesting. Huh. What happened there? What happened there? Negative 97. Uh-oh. 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 What's going on there? Uh-oh. That's not what you expect. Okay, so current index negative 97. C is a non-printable character. Current index is 24. Now, how did that happen? Zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See. So the character to the right is 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Ooh. Ooh. That's out of bounds, sir. That is out of bounds. Ah, duh. That's my mistake. That's a very simple mistake on my part. Also one that I was not expecting. I tend to forget to do that from time to time. If you're greater than or equal to that final bound is what you need in order to ensure that you do not. Yeah, okay. I thought I covered that case. That was why that was so difficult for me to. I thought I covered that case. So difficult to find it, to see it. What a surprise! What a surprise! There we go. Okay. I guess we did it right. I don't know. Ready for this one? Lots and lots of prefixes. How many characters do we need? We need 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. How about that? How about that? Oh, grids to have equal length of rows. Excuse me? Wait, what? Are you kidding me? No. What? What? Is this some kind of sick joke? Is this some kind of sick joke? Brother, I just spent so much time trying to figure this out to make this efficient if you have prefixes. And you're going to tell me, you're going to sit there and tell me that all the words need to be the same length? Are you serious? Is that a joke? Is you serious? Is you serious? Is this for real? Is this for real? Brother, I'm gonna lose my mind. What? I don't know if I should say that publicly. I get in the habit of saying that. Are you serious? Are you absolutely serious? Are you absolutely serious? I can't believe it. I hate everything about software development. I hate it. I hate it. I wouldn't say hate it. That's not true. It's just the things like this is just infuriating. Brother, are you kidding? Is this real? Is this some kind of sick joke? Is this some kind of sick joke? Oh man. I don't know. I think, well, there's probably an optimization you can make that I'm just not going to use now because, is this real? I think it's real. I think it's real. Grid words to have equal length rows. I'm gonna lose my marbles. I'm losing my marbles. Excuse me. This can't be real. This cannot be real. This cannot be real. By the way, that removes the problem of prefixes altogether. So that just that makes this problem so much easier. You gotta be kidding me! Ah! I can't believe it. Oh, and you're saying to me, oh, and you're saying to me, I can't believe it. Ah! There's gotta be a joke. There's gotta be some kind of joke. No! 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 99999! 99999! Nicht 999! Brother, this is sick. This is sadism, is what it is. This is. I think I is also. I think it's related to God. Oh, my phone is dying. My phone is so upset that it's hurting itself. That's what's happening. I spent like a week on this problem, man. I spent like a solid week. I spent like a full week trying to figure this one out. And I was like, look, man, there's no way. There's no way we could do this efficiently if it has prefixes. It can't have prefixes with that condition. That would have been a good condition. Oh, it does say that. Oh, it does say the same length. I'm so upset. Oh, that's just upsetting. Dude, that is so upsetting. It says that. It says that. I gotta start all over again. How come? I don't know, man. I have such a hard time reading things sometimes. Like, you gotta read the conditions so carefully. Because I don't know, I just kind of skim it quickly. I'm like, oh, I get the basic idea, and then I read the constraints, and I'm like, okay, I have an idea of what they're going for. I don't know, man. It's like constantly a problem for me, especially the hard, like all of the questions. Really, they're so much easier if you read it. If you read it. Why do I have such a hard time reading? I don't know. I don't know, man. I think I'll remember that. If I get stuck, just read. I think what I should do is just read the question like 4 or 5 times and just read each sentence carefully. Just slowly read, not carefully, but slowly read each sentence until I get it. If I don't get the answer, yeah, okay. Especially if I don't get the answer within a few hours. Oh, that is painful. That is just upsetting, brother. That is just. If they're the same length, then you can't have prefixes like that. No, sir. No, sir. That is just frustrating. Ree. Ree. Wow. So. Lives in a pineapple under the sea. Dude, I'm just upset now. I would say this is just legitimately upsetting. That's what I would say about this one. I would say it's just legitimately upsetting. All right, we're gonna try word good best word. I'm gonna work through that example again. Try to find. There's gotta be a way. There must be a way to solve this. That's relatively efficient. My brain is just mush now after all this. This is like. Oh, I can't believe I missed that. That is just depressing. Oh, the same length, they say. Oh, okay. Okay. Just happened to miss that. Alrighty. So word, good, best word. Alright. Word, good, best word. And then the words are word, good, best word. Word, good, best word. I mean, I'm just upset at this point. I'm just upset. You know, I'm just upset. Just gonna say that I'm upset. That is legitimately upsetting. That is upsetting. That's upsetting. That is upsetting. So now the question is, well, I could still use a try from the beginning, but then the question is, I want to say once you've made the first check, then you can reuse that with a Q. You just have to make sure the next word you see is equal to the first word in your queue, and just pop from the front of the queue and add the next word. I think at this point then you can actually just use a queue and a frequency map, because yeah, if the next word, they're all the same length, right? So that means a couple things. First off, the word itself needs to be divisible by the word length for this to work. Well, no, that's not necessarily true. There might be some. No, that's not necessarily true. Yeah, you could just use a frequency map, I think, of the words themselves, and then use a queue. And what's interesting is it possible for the words? So I think the issue of like prefixes could still be a problem, because let's try something like a little. Yeah, I have to like think about it all over again. Oh, it's upsetting. This is just upsetting. You could do something like this. All right, let's try this one. So we won't have any prefixes anymore. Yeah. So this code is correct, but I think it's inefficient, right? Because let's do okay. Let's try this. Let's do 10,000, and the most we can get is we could do 3,000 of these A's, just A 3,000 times, right? We could do, yeah, so let's try that. Let's try to generate this test case. Let's see how slowly our code runs, because I think it'll be kind of slow. My thinking is that it'll be kind of slow. So we could say awk, just echo awk, print hello, or we'll just say end, print hello. Does that not do what we want it to do? How do we? Isn't there a way to do this? Huh. Oh. Okay. Why is this not working? Okay. Okay, that's what I was looking for. All right. You don't need to. Oh, well, yeah, you could do this. It's fine. So we're gonna say for I equals 0, I is less than 10,000 plus plus I. Have another loop that we run, and that's going to be, we're going to say x equals x concatenated with a, character a, and then at the end of this, end print x. Hold on. Okay, print hello. Excuse me. Can we just print x? Oh, that's probably why. It might have something to do with it. Hey, there we go. Okay. Okay. Now we want all of these A's, triplets of A's. So we want 3,000. That's fine. We don't need to do more than that, I think. Well, 3,300 is fine too. 3,300 of these, and we're going to do AAA, comma. Oop. Copy that. Paste that here. There we go. All right, let's run that piece of code. Run that test case. Invalid test case. Not, oh no. Made a mistake. We need these to be strings. There we go. That should be better. All right, try that now. Let's try that now. Let's see what we do. TLE, okay. Valid test case, valid test case, yet invalid solution. So there is a faster way to do this with this condition, with this problem. But what's interesting is, excuse me, a simple Q solution won't quite work the way we want it to. Well, maybe you can run the Q-based solution sort of left to right from each index. What would that do? What would that look like? By the way, I think the reason this is so slow is not because... I think the only reason this is so slow is that we just need to check for, well, I was gonna say we just need to check for, like just do a size check. So something like the following. Count the, well, upper limit, we'll just say. Total, or sum of words. Or words count. It's going to be equal to words.size times words of 0.size. And then we're going to say minus this characters count. So this is, I think it's still correct, but let's see. If the, oh, it's wrong now. Yeah, I was gonna say I think I'm off by one. It's not correct. So the size is the number of characters, and the characters count is a number of characters. What you need is I plus the characters count minus 1. It's got to be less than the size. And the reason for that is that you take I, you're going to include, yeah, I think it's a minus 1 you need. And I'll explain why in a second. So I plus all the characters that you need, I plus all the characters that you need wait a second. I is an index. If you add all the characters that you need, you still need to be less than the size. Less than or equal to the size minus 1. Because that's an index, and these are characters. You're adding index to index. You want to, yeah, that's why. That's a tricky thing. That's so tricky. When you're comparing indices, you're okay. But if you're comparing indices to counts, the counts are 1 indexed, whereas the indices are 0 indexed. So you got to subtract. The general rule is to subtract 1. But the reason why it's confusing is that this size is a count as well. But really, you would do less than or equal to minus 1 to get that to compare correctly. And then now these are all indices that you're comparing to each other. And now it works nicely. Which is interesting though, because you could subtract 1 from both sides to make it less than or equal to, or add 1 to both sides, and you have this now, which is even more confusing, which works as well. But yeah, we don't want to do that. We want to less than the size. So yeah, that's a little confusing, but right, obviously this now is reasonable in terms of runtime, but you can actually make this less reasonable in terms of runtime. And I think that'll break it. We're trying to break our code. That's the objective here. Because if this works, I'll just submit this and move on. Because it's like, what is the point of trying tormenting yourself trying to figure this out after I spent a week on the wrong question? All right. So we're gonna go through halfway. Right now, this is gonna be a little more interesting. If we go halfway, so we do 10,000 divided by 2 divided by into 3 pieces. So we go 1, 6, 6, 7. Now you might think, how is this going to be slower? But I say to you, watch and learn. Watch and learn. The reason is that the smaller this is, the more loops need to happen here. And I think in that case, it actually will take more time then. See? Told you. Told you. That's the problem. That's the problem that I had before too. I was like, I think no matter what I do with my solution, no matter how I make things, this is going to TLE. Like, this is just always going to be too slow. So there is a trick. There was a trick. The trick is we're supposed to use no prefixes, basically. All right. So the solution that I have just won't work in this case then, because you're going to end up doing was that 1667? You're going to do that. Multiply that by 5,000. And these looping structures are not particularly efficient either. We're looping through a try with an unordered set to reset each time, so it ends up being pretty expensive. Yeah, this is like a few million or something executions, or different iterations. So you might have noticed though that this particular problem could be solved very quickly by just noting that, well, the number of A's you have, it's the same repeated thing over and over again. So the number of A's you have is 1667. You could actually do this by hand. There's 1667 of these things times 3 gives you 1, 2, 8, 0, 2, 8, 0, 2 is 5,001 characters. And so they're all there's just 5,001 A's straight across, and you could take 10,000 characters, subtract 5,001, characters, you get 4,999 characters. We could subtract 1 from both of these to get indices, so you would get, if 10,000, the index would be 9999, 5,001, if those were indices, you get 0 to 5,000. And so you actually get the same result, but so the last index that works is going to be I think 4,999, right? Because you can have 1 character there, and then maybe if you put that index to 0, then there's 1 character there, 5,000 characters to the right. If you added 5,000 characters, you get 9,999, which is exactly, I think that's correct. So that's the last index that works, which means this actually has 5,000 solutions. Right, the 0 to 4,999, those indices, all those indices will work. 4,999, if you add 5,001 positions to the right, you get to 10,000. But if you include that position, you only add 5,000, then you have enough. So yeah, so you do that by hand, you'll have 5,000 for this solution. However, that's not how we do it in general, and there should be a more general approach that will still be relatively efficient for this one. I'm thinking some kind of a queue-based solution should work. What you can do is you could take an index, and so I want to say there's like O of 30 times n, so which is O of n, and just say basically you're going to make a queue starting at each index. From left to right, you create the queue if there's a match, And then what you're going to do is if there is a match, you're going to loop, you're going to pop from the front of the queue and push it to the back of the queue. And you're just going to keep processing each new word from there. You use the try to determine whether or not it's a new word, and you could also update the totals in the try. And in this case, that'll give you every. So you only have to really run that 3 times, right? In this case, it would be O of 3n, because it would be linear, right? Only processing each character once per quote unquote queue execute queue run, I guess. And so you'd have 3 characters, another 3 characters, another and at some point you get a match, and then now you start popping from the front of the queue, and trying to match that against the next 3 characters, and you just keep doing that over and over until the end. And then if you have, then you would start at the next index and do the same thing again. Now, I guess what you would do is you could use a vector of booleans to check which indices you've already started with, and you could loop through every index. But what can happen is, so obviously this would be sort of one of the most expensive case, or would have otherwise been one of the most expensive cases. This one will be, just O of n, basically pretty relatively efficient. There are cases though where things don't line up so nicely and don't work so nicely. I think what you would do is you would execute this on every index that hasn't already been either processed or doesn't have a solution. So one issue though is, now what if all the words are different and we start just kind of processing things in this way? Basically we're trying to just reuse the previous characters each time. That's really what we're trying to do by using the queue, and I think that does work nicely. It's just the problem you can run into is like you could kind of get stopped dead short where you can't reuse anything from the previous queue. I think what happens is if you, let's say you get a match somewhere in the string, and then you want to pop the previous word in the front of the queue and then add that word to the front. Well, you know that if it fails, not only is that particular index not gonna, like the index that you popped to, I guess, quote unquote pop to, not only does that index not work, but also the problem you'll run into, and there are a few questions here, is like, is it possible to rearrange the matches that you had? No, it's not. No, the only things that'll be prefixes of each other will be, or suffix, even, well, it could be something with a suffix, but you don't have characters of different lengths. The only prefixes you have are words that are the same. Yeah, I think all those issues kind of break down because you really can't partition the words into different ways now because they are the same length, all of them. So yeah, again, any word that's a prefix of another word is going to be the same word. So that kind of breaks down too, which is nice, helps us. So then the question is, does that mean that all of those indices fail? Not necessarily, because you could pop another word and then actually, yeah, you could pop another word and those 4 characters that you processed could be one of the words that you just popped, right? So if it's not though, then you do count that. Yeah, so you could pop the queue left to right, and each of those indices you could process. So that actually does work. So you can say with certainty this is O of 30n in the worst case, right? If all the words are of size 30, then you have an issue of so you can process all so you can process sort of as sort of a modular way, like every index modulo 0, every index modulo every index of S modulo we'll call that we'll call this K, or what do they call it? They said we'll call this K, the words length, modulo K. Every index like 0 modulo K you could process in one iteration. What it comes down to is basically you would do is you would process each word as you can, add it to your queue, and then once you see a spot where you can't add that word anymore, then you say you failed at that index, or even if you make a match, either you fail at that index or you make a match. But let's say you fail, then you could pop your queue until you're not failing, right? Presumably you would that word would be something that now actually if that word is not so you can actually speed things up a little bit too. So slight optimizations here. I don't know how efficient it would make things, but you can optimize a little bit where you say if that word is not any of the words that are possible, then the problem you run into there is no amount of popping is going to get you there, get you that word. So all of the indices up to that point, you can clear the entire queue. All the indices up to that point would be failures. You can mark them as failures, and then you can go to the next word, and you have a similar thing, right? If that is not a word, then again you just fail, and you could just keep going. So, but if you do end up getting a, so if you go through your whole queue and you get sort of success all the way to the end to get a match, right? Then that index would be considered a match, and then you check the next word. Now again, the next word, if it fails, the slight optimization here is that you don't have to keep checking that word over and over. If it fails all of the words, then it fails all of the words, then you can just pop everything down and write them as failures. If it's one of the words one of the duplicate words, and you need to pop until that duplicate word is seen again, then the optimization would be you can actually immediately pop all of those down, and and then sort of begin at that new index that you're at. So yeah, you can get this to O of 30n definitely, which is O of n. So you can definitely get this to O of n. It's a little tricky, a little bit involved. It uses queues, and I guess try is good too. We could use a try and a queue and a frequency map, and the frequency map is kind of built into the queue, or the try. You don't actually need to use a try anymore though, because you could just use a frequency map, because these characters are like you can use a string builder, I guess, and just build the strings as you go and check them in the frequency map. I think that's probably better than trying to walk through a try. It might be more efficient to walk through a try potentially, but not that much more efficient, I think. Yeah, I don't think so. I don't think it's really worth going through all that effort to make the try. Maybe it is. I could be wrong. Well, we already have the code to make the try, so we might as well. You could use the try to determine whether or not the next string is something in the frequency map. Yeah, actually, I think it's better to use a try. I think it's a little bit better to use a try. I think It's not terrible to use a regular string, but I think for efficiency's sake, because I think it's a whole potentially a whole factor of like 10, like 30 times faster, 30 times slower, roughly. If you use the try versus a regular string, because I think the string, you have to build the string piece by piece, and I think that's not the most efficient way to do things. And have to rebuild it every time, which is kind of unnecessary. Let me think about that. Yeah, I don't know exactly how the string builder works underneath. I want to say the string builder is a lot like if you're manipulating arrays, that it would be sort of more efficient because you're sort of like manipulating arrays instead of strings, where strings are immutable. So if you create strings, it can be a lot less efficient because every string you have to create a new one that's immutable. But kind of curious. Excuse me. Or string stream, not string builder. Think Java as a string builder. Input and output operations on string-based streams, stores instance of the string and performs the input operation on it. Low level wraps a raw string device implementation into a higher level interface. Clean interface is provided. String buff is a basic string buff whose associated character sequence is a memory resident sequence of arbitrary characters which can be initialized from or made available as an instance of basic string. The typical implementations of string buff hold an object of type basic string or equivalent resizable sequence container directly as a data member and use it as both the controlled character sequence, the array where the 6 pointers of the string buffer point to, and as the associated character sequence, the source of characters for all input operations and the target for the output. In addition, a typical implementation holds a data member of type iOS base open mode to indicate the status of the stream, input only, output only, input output at end, etc. Over allocation strategies used by overflow, an additional high watermark pointer may be stored to track the last initialized character. 2 specializations for common character types are also defined. So there's string buffer and wide string buffer. Overflow, interesting. Oh boy, it's a lot of functions. A view, underlying character sequence. So what I want to do is actually test this now. Maybe I can test something locally. I need to eat food though. You know what I'm gonna do? I'm gonna stop here. The temptation is to use a string stream. Excuse me. In order to not need. Yeah, in order to. So the temptation is to use, and maybe we'll use maybe we'll just use a string, a basic string. Because I think the implementation underneath of the basic string, like I think a C string is a little bit different. A C++ string is a little bit different than other strings in other languages. Excuse me. I think it's a little bit more efficient if we use a regular string. I mean, it's not more efficient, but it's as efficient as we need it to be, I suppose. Because strings are mutable in C++, so it's a little bit different. Yeah, so I think we don't incur that extra overhead. I think string literals are immutable, but strings themselves are not immutable, which is a little bit confusing. So I think we don't necessarily need to do any string building, quote unquote, to get the efficiency that we want with our C++ strings. One thing to consider though is so then we could just use a basic frequency map, and then actually we can even update our frequency map slightly so that way it's not really a frequency map, but it's actually has a stack of indices where the next word is that we want to use, and so we could pop the words until we get to that index, and then set all of those indices to sort of false, and then pop that word in that particular index, or update, pop that word, get to the next index, and then we know what we just matched. We can push into the queue and continue potentially pushing things into the queue. Yeah, very interesting. And the vector of things that we already have viewed or already processed, we just say, if this is in the range of things that we want to process and whether or not we've processed it, that's just to keep track of our, that's sort of just like our modular arithmetic. We actually don't even need to do that, I think, because I think we can just run an iteration for each of the sort of starting characters, right? And that actually would be sufficient. Yeah, that's actually fine. Very neat, very interesting. Yeah, so there's a queue-based solution. I'll just say vaguely, there's a queue-based solution using a frequency map that we can run to get this to be O of the length of S times the word size. Call this K and call this S, not S, T. Call this T times K, O of T times K, or O of N times K, which is efficient enough, right? That should be 10,000 times 30 is plenty efficient. So I think we can come back and solve this problem. I'm going to take a break. We'll come back to it. Have some ideas now, better ideas. We don't need to use depth first search or anything. I'm really annoyed though. I'm really annoyed that I misread this and spent like a week, like almost a full week, just trying to figure out how to solve this. That is absolutely infuriating, really frustrating. So yeah, that's 2.5 hours now that we were just kind of trying to think this through, and it's always good. It's always good. So yeah. We do need to keep our we could have a frequency map, and then we could have a map of stacks, or I guess that'd be queues actually. How far to pop to. Yeah. That all of it all together should still be linear time. Yes. The only reason you have the frequency map is that you need to know how many of each word, what the limit is. So we would know that if we found a word that it's in the map, but it's I guess, a copy of it. Whether or not we can just plop that into our stack, or for that particular word, or a stack of indices, or have to pop from the front of our queue until we can. Actually, it's not a stack; it's a queue. Sorry, it's also a queue until we pop one off of that queue for that word. Yeah, pretty interesting. Yeah. All right, I'm gonna go. Thank you for watching. I'll talk to you soon. That's our part 2 for this. It's brutal. That's upset. I mean, that's just upsetting. I would say that's just outright upsetting. Oh. Gotta learn how to read. I need to read. That's the problem. I don't read the problems. I don't process them. There goes my whole trying to solve 12 hard problems a day. Trying to solve them once every hour. That's what I would like to do. Ideally, if I could solve one per hour, then I can just fly through these. The hard ones are really the ones that are particularly difficult. The medium to easy ones I could probably solve in 5 to 15 minutes, depending on. The easies are probably 5 minutes. The mediums are probably 5 to 30 minutes, and then the hards are usually at least an hour. But sometimes I'll just get totally blown over, like you saw here, and just get stuck and it's upsetting. That's what that is. That's just upsetting. All right, thank you for watching. Talk to you soon. I don't know. Maybe later today I'll come back to this. I might just need a break for a while. Just grieve, and then come back to it. All right, yeah. Thank you for watching. Talk to you soon. Take care.